Solar NUV telescope on board upcoming Aditya L1 mission, and also performed substantial work on long-term study of the Sun using multi-wavelength historical datasets. Shubhamay has more than 15 papers published in international peer-reviewed journals. He is currently a postdoctoral researcher at Southwest Research Institute. He is working with Andres Munoz Jaramillo on novel application of machine learning approaches in varied heliophysics problems such as homogenization of multiple surveys, solar event detection, and space weather prediction. Today, he will be speaking on leveraging a convolutional neural network to efficiency level a Flux Emergence video dataset. To Shubhamay.
Thank you, Mushumidi, for the kind introduction and giving me the opportunity to talk about our recent work. So just wanted to ask you if you all see my screen clearly and hear me loud and clear.
Yes, we can see.
Yes.
Okay. Yeah, so this is a very recent work that we have performed at the Southwest Research Institute. So this is about how to utilize a convolutional neural network to efficiently level a solar flux emergence video dataset. And this is funded by this NASA grants. So this is the brief flow of my talk today. This talk will be focusing on solar active region evolutions in form of videos, and it will start with iterative refinement of data levels. So these videos are crudely leveled using an available catalog, and then we develop an iterative method to gradually refine the crude levels and come up with a very high quality level for each of these videos. And then we also design a model ensemble approach to identify the uncertainty in classification of those videos. And at the end, we repurpose this approach to perform a higher level task, which is frame leveling. So initially it is a classification problem, and then we repurpose the trained model to identify where in the videos the emergence happens. And this entire work, the backbone is deep learning, especially a convolutional neural network. So before I come into the actual work, let me give you a brief background of why deep learning. So if you look at the classical machine learning models, let's say we want to solve a particular problem here, given a data set consisting of different vehicles. We want to classify each image into either a car or not a car. So if you apply classical techniques, what you will require is a feature extraction step, which is also called feature engineering, to take an image and identify different features that best describes the image. And for that, you need some manual intervention, right? You need to think what features are good enough to arrive at an inference, and you may never reach at a good enough set of features, right? That's the limitation. But when you involve these deep learning methods, you get rid of that feature extraction step. Instead, you can directly put the images to identify the most important features to arrive at an inference, right? So let's now try to understand how it does that. So on the left, what you see, the picture of a dog, okay, and this is what we want to build is a classifier which distinguishes between cats and dogs, right? And so what you can say, okay, instead of feature engineering, we can use each pixel of the image as a feature, right? So let's say this picture is 1,000 pixels by 1,000 pixels pictures, right? So we will have 10 power 6 features, input features. And now suppose we have again 10 power 6 hidden units, okay? So the number of connection that you are going to have is 10 power 12. So now you can clearly get an idea that when you have complex data set involving such large number of pixels per data instance, you will clearly put a lot of burden on the computer memory, right? So what you want is you want to reduce the computational burden. So, and also when you are talking about the structured data such as images and videos, it often happens that the features are locally correlated. So the scientists found the optimal way to use these locally correlated structures in images is to use convolution, right? So instead of connecting each of these pixels to every node of a hidden layer, what you want to do is you define a convolution kernel that you multiply and add across the image and shift, and then what you do is you try to learn the coefficients of the convolution kernel instead of learning all the connection from pixel to each of the hidden nodes, right? So it is every kernel is looking at a limited field of view within the image, and also the weights are being shared across the image. So that's the approach of convolutional neural network, and this is here a particular layer of this model. And when you cascade many such layers with nonlinearities and downsampling, what you arrive at is a convolutional neural network. And also with that architecture, another interesting phenomena what happens is, so when you have these layers and you have many such layers, right? So what you will see is for the earlier layers, you are discovering the lower level features, such as for the cat, you were looking at the edges, curves, all the lower level features. Then when you go deeper into the model, you join these features, right, to learn about the higher level or abstraction of this image, right? And then you keep joining this, and you at the layers towards the end, you identify the entire face of the cat, right? So so these are basically the structures that are being learned by the convolutional kernels. And higher you go, the kernel covers a bigger field of view, and which in turn returns a more complex feature, right? So these layers actually represent the hierarchy of features that are discovered totally in automatic manner by these deep neural networks. So now with that, we come to the kind of data we want to deal with. So we can now understand why deep learning is important to identify patterns in such data set which are both temporally and spatially heterogeneous. So you can see the sun in an extreme ultraviolet wavelength, and you can see how things are changing over time and space, right? So the problem we have is the following. We have this magnetic patches identified from Solar Dynamic Observatory Michelson Doppler imager, projected into Carrington grid into 15 degree by 15 degree patches. And these patches are stacked over half a solar rotation. Okay, and the two consecutive patches have a time difference of 96 minutes. Right. Um, so what we want to do is we want to create these videos and identify within half a solar rotation whether an active region just evolves within the temporal span, or you see new emergences, right? So what you are trying to see the evolution of active region within the span of the temporal span of the video, whether you are seeing new emergences or you are seeing pre-emergences that is just evolving over the time. So on the left, what you see, you don't see anything at the beginning, and then when time progresses, you see this clear emergence of bipolar active region. And then on the right, what you see is an already emerged active region. You are just seeing the magnetic arrangement is changing, but there is no new emergence within the temporal span. So you want to classify, or you want to distinguish between such videos, right? So our problem is to design a binary video classifier. So given a video of solar active region evolution, we want to say whether an emergence has happened within the video or not. And these are very interesting events, because these often get the potential to modulate the space weather. So we have in our dataset around 2,400 videos over the years 1996 to 2011. That is the MDI era, and they have every frame has 90 pixels by 90 pixels, covering 15 degree by 15 degree in Carrington grid. So we use Carrington grid because we don't want the active regions to shift or drift over temporal span. Okay, but of course we don't nullify the differential rotation here. And then we have the time axis to 25 frames. And another important factor is there might be missing frames in these videos. So when you put this video as an input to these models, they're totally blind about the timestamps, right? So before using these videos as input, you need to ensure that they are interpolated in time, or you have always the same number of frames, and also the time step is constant for every video, right? So what we do is we identify the missing frames with their timestamps, and for each pixel we do a linear convolution along the time axis to fill the missing frames. And by that we ensure that every video has uniformity in terms of time steps, and also they always consist equal number of time frames, right? So now to train a supervised deep learning model, we need to have levels for each of these videos, right? So we acquired those levels, or what we call these levels as crude levels, from the BART catalog developed by Munoz Aramilo et al. And so this catalogs uses different morphological image processing techniques to identify bipolar active region from full solar disk of MDI line of sight magnetograms, and it identifies the active region once every day, right? And so you can understand that why this is crude in nature, right? So you are only identifying active regions in 24-hour interval, and if anything is happening within and disappearing, you are not capturing that. Also, you put this hard longitude cutoff in this for this BART levels, assuming that anything before this cutoff is a returning active region and thus is a non-emergence, and anything after that can contain both emergence or non-emergence, right? So what we attempt next is we try to refine these crude levels by training an ensemble of neural networks. Okay, and this is the architecture of the neural network. It takes input videos, which are of the size, again, 90 pixel by 90 pixel by 225 frames, and then this applies convolution with 3 cross 3 kernels. So every filter has this 3 cross 3 uh, uh, size, and also this transforms this input video into this 90 by 90 by 32 cube. So this 32 here is the number of feature layers, and in each of these feature layers, the input video temporal frames are getting fused, right? So from the video, you are discovering 32 different features with 3 by 3 convolution kernels, and then you apply nonlinearity and repeat this process, and you also gradually decrease the size of the frames by increasing the coverage of spatial coverage of each pixel. And when you repeat this process again and again, you gradually vectorize the input videos, and then you apply this fully connected uh, layers to arrive at a single number, which is the classification outcome, right? And then we use this minimize this binary cross entropy loss function to train this model. Okay, and so what I said is also, apart from the convolution, the nonlinearity is important, because if you did not have nonlinearity in between, it will be just cascade of linear operations, and which will be then redundant. You will not be seeing new discoveries per layer, right? And there is no point of having multiple such linear operations. So this is the architecture, and then this is how we create the ensemble. So we have this entire set every year from January to October, and we keep aside a test set which covers November, December every year from 1996 to 2011. So we don't touch the test set, and we just divide this first 10 months into non-overlapping validation blocks. So they are disjoint, but when you combine all the validation blocks, it covers the entire data. And so, but the training set will have this overlap. So for the model one, the validation set will become a part of the training set for model two, right? So that is how we design this training validation combination to train a set of 5 models. So once you train this 5 models, you make the models to look at the corresponding validation blocks, and you identify where the model disagrees with the original crude levels, right? So when we identify those disagreements, we manually check and correct if there were problems in the crude levels, right? So that is your one iteration, and we use that verification for each of the validation blocks. So when you do it for all the validation block, you cover the entire data set. That is the idea of arranging the validation blocks like this. And once you do that, you repeat this process. So here, so in the first validation block, you found some problems in the crude level. Then in the next iteration, that goes into the training set of model of every other model, right? And this applies for any other training validation combination. And so when we do these steps over several iterations, we observe certain convergence. This is the iterative process, and the results we find with this iterative process. So we had initially this crude data set. We train the model. So this pass one is the first iteration, and then we look at the disagreements, right, where the convolutional neural network inference is different from the crude level, and this yellow region are the ones where the convolutional neural network was correct, uh, and the disagreement was because of the problem in the crude level. So it does correct the crude levels. And the blue region corresponds to the videos where the convolutional neural network was wrong, but the original levels were correct. So we keep those unchanged, right? Now, once we do that for all the validation set, we train the model again, model ensemble again, and we repeat this process. But when we for every other iteration, we don't look at the videos which were already manually verified in the previous steps, right? So when you go ahead with this iteration, what you start seeing is among the new disputes, a larger fraction of more videos go in favor of the CNN, right? So it will always happen that the convolutional neural network will make a certain set of mistakes, so which affects the accuracy of the model. But the new discoveries or new disagreements will gradually come in favor of the convolutional neural network. So by that, it is actually hinting that the model is learning to generalize on the dataset that it has not seen before, and also it is understanding, also your data set is going to get refined to an extent that it is driving the networks to learn the correct things, right? And also when you look at through a different perspective, so these different colors represent different iterations again, and as you go to higher iterations, as you can see, the model ensemble performance comes closer to each other. So the highest pass here is the gray one, and you can see they are much closer to each other than where it started, apart from the improvement in the accuracy. And also in the y-axis, what you see is with higher iterations, the requirement of changing those levels will go down. And also in the new disagreements, most of the disputes will come in the favor of the model. So it will just say that whatever new disagreements you find, just you can blindly trust the model, right, when it reaches the optimal accuracy. So in a nutshell, we start with 2032 videos, which had a set of a number of mislabels, which is 650, 32% of the total. So this we found when we manually verified each and every video to validate our process. And then after 4 iterations, what we found is we corrected 550 of mislabels out of the 650 mislabels, which is 85% of the total number of mislabels. But through this process, we manually verified only half of the total set of videos. And so uncorrected mislabels remain at 100. Right? So what it is hinting at is this iterative process that we developed can accelerate the labeling process, minimizing the human intervention. Right? So now looking at the next phase of our work, which is uncertainty. Okay, and I wanted to give you an example why model ensemble is important, right, and why uncertainty estimation is important. So here we have again a binary classifier that is supposed to see 2 different faces. So these are the x-axis; those are the faces that the training set contains, right? And now, if you provide the model to classify a face which is represented by the training set, it will be confident, right? It will classify that face to one of these classes, which is fine. But suppose you provide another face which was not shown, right, which is neither of these 2 people, to the model, and ask the model to classify into one of the classes that the training data consisted of. So you would expect that the model, as the model did not see such face, it will be quite neutral and it will give a probability of 0.5 for both, right? So it is quite confused. But in real, what you see is these models will be pretty confident, and the result will be wrong, right? It cannot be either of these faces. So this is the danger of believing in a point estimate of these deep learning models, right? So even if you think of forecasts, right, for different space weather applications, suppose you are forecasting solar energetic particles. If the model is very confident, right, or it says that there is a very high chance of ACP happening. So then now the question is whether you can trust in the model or not, right? You may trust, and in real it may happen that ACP does not occur. So what you really want to understand is what is the uncertainty in this prediction, right? And this uncertainty is important when you have such small data sets, right? When you have small data sets, your training data will not be representative of the entire space of a data set. So instead, what you want is an ensemble of models, okay? And there are different ways to train an ensemble of models. Suppose we have an ensemble of model, and we ask the same question to each of the ensemble members, right? So now when you show the model ensemble, the face which was represented by the training set, you see that the spread or the disagreement between the ensemble members is quite less. But when you show a face which was not a part of your training data, which is totally dissimilar from your that space of data set that was covered by the training set, then you see the huge disagreements between the models. So this is the advantage. So instead of believing at a point estimate, if you look at the uncertainty, you can totally take a judicial decision, and you can say, this spread gives you a hint of how trustworthy is your prediction, right? So again, to train our model ensemble, we initially take out another set which is called a benchmarking set for tuning the ensemble prediction. So we we in the very similar way that I was showing during the iterative relabeling process, the first 8 months you would divide into 4 non-overlapping validation blocks, and the rest being the training set. And for each of these models, you train another model utilizing a different random realization of the dropout. So dropout means when you are dropping different neural network connections randomly, and this is done um, to regularize the models so that the model stops overfitting and it starts understanding the general patterns of the data. So this is what we do initially, and then we use a benchmarking set to identify a classification threshold by choosing an optimal point of the precision recall curves. And then once we do that, we expand our training set by including September and October, and then we have 5 models and a pair of models for each of these by changing the dropout random realization. And we have now a set of 10 models, and we have again the test set which is not touched. And this is what we get, right? So we have on the x-axis the video indices, and on the y-axis we have the score, right? That is like the probability of emergence for which is predicted by each of these models of this ensemble of 10 models, right? So this is a 2D histogram. So x-axis you have the video index, and y-axis you have this bins of probabilities within which the gray levels say how many models are predicting, right? And then we calculate the median of each of these videos ensemble prediction, and we see if the median is above a threshold which is 0.6, which we found by precision and recall curves. And then we separate these true positive, true negative, false positive, false negatives into 2 different regions called unstable inference and stable inference. So unstable inferences are the ones which in which the models are not very certain, right? So you can see that within the spread of this model inferences, you have the classification threshold. So they are not very certain. So that is, even though the median is above the threshold, right? So that is where we put this unstable tag, and the stable ones are where your models are agreeing in a better way to each other, and most of them are above a classification threshold, right? So you can clearly understand the value here of using the model ensemble instead of using a single model. So if you used a single model here, um, even here you can see different outliers, right? So outliers can be quite confident, and your actual occurrence can be quite different from what it is thinking. So you are just utilizing the spread of this ensemble prediction to understand or to identify how much you can trust on the model predictions. And when we now divide the test set into blocks of 2 years and evaluate the classification accuracy over the entire MDI era, we don't see any modulation caused by the solar cycle phase on the classification accuracy. And then we come to the next phase of the work, which is, so now that we have trained the model to identify if a video has any new emergence or not, can we identify when the emergence happens in the video? So this is the repurposing part. We don't train the network to do or perform this task. Instead, we use the trained classification model to identify when the emergence happens. So for this, what we do is we gradually mask frames, right? So here what it is showing is we truncate from the end every frame until the 1/30th frame, right? So after truncation, we just replace every other next frame with the 130th frame, and pass this new video through our trained classification models and record the inference. And we do this several times, increasing the truncation, right? And when we do that, um, we see this. So we have these videos. These are truncated differently, and at every phase of truncation, we evaluate the video through all the ensemble members, all the 10 models. So you see that. So and this is color coded according to how many model at each phase is thinking that this video corresponds to an emergence. So when you start this video, it is blue. Of course, there is no emergence happening. And at this point, you see. So if you look at this color bar, at this phase, only 2 models were thinking this is an emergence. When it will go past that, most of the models start thinking that it is an emergence, right? So this is the value of, again, this ensemble approach when you are repurposing this model to perform a higher level task, which in this case is identifying the epoch of emergence. And as you can see, it becomes more higher in the color scale as you go ahead, right? Now if you look at how the model inference changed as a function of the truncation, you can see after a certain point, when you go past the epoch of emergence, the ensemble median prediction goes below a certain threshold, right? So there is a transition from the model ensemble saying yes, it is an emergence, to no, it is not an emergence, not a video which contains emergence. And that transition gives the epoch of emergence, right? So what we do is we calculate the gradient of probability and identify where the gradient is maximum, and label that as the point of emergence. And when we do this for a set of manually verified um, bipolar or multiple bipolar emergence videos, on the x-axis you have the ground truth time in days, and on the y-axis you have the identified time of emergence. By this model repurposing, you can see a more or less linear fit. But you also see another. So when you subtract the ground truth time from the predicted time, you can see that there is a small shift from 0 in the histogram of these differences, right? So x-axis you have the video index, y-axis you have the difference of identified and predicted time, and you can see that from 0 the peak is little shifted. So we are yet to understand why that is happening, but this may be because we did not tune the model to perform this particular task. This is only the result of repurposing the model and then identifying those gradient of probabilities as you increase the truncation. When you actually train the model to do this task, maybe we can bring this shift back to 0, right? And also this repurposing gives provide us to a sanity check, right? So if the model is able to identify the dynamics in the data. So if the model was not able to identify the temporal evolution of those active region emergences, it would not have identified the epoch of emergence, right? So it also says if the model is saying yes, it is an emergence, it is actually saying that for the right reasons, right? It's actually understanding when the emergence is happening. So now that the model is able to identify when it happens, this is another analysis to understand if the model is also looking at the right place. This is called the Saliency Analysis. So in this, what you do is you keep the trained model frozen, and then you change the pixel value of different frames in the videos to understand which pixels are more sensitive, right? So you have this output score of the model which is more sensitive to the change of certain pixels, right? So actually what you are getting is a pixel wise map of derivative of the class score class code here is you can think about the probability of emergence produced by the model. So how the derivative changes across the frames with so derivative with respect to the pixel intensity. So the brighter regions say that a little change in the pixel value will create a large change of your class score, right? So the derivative is much higher here than anywhere which is darker than this. So, and now if you look at the identified frames of emergence, right, from the median of the model ensemble, you can see that there is a direct overlap between the saliency map and the and the and the bipolar region state at the median frame of emergence, right? So this also says that model is giving importance to the site where emergence happens, apart from also the epoch when emergence happens, right? So both spatially and temporally, it is looking at the right place. So now to summarize our work, so we have seen that we did not need to look at the entire data to define the leveling. We looked at only 50% of the data to correct 85% of the mislevel. So that is the value of using the model itself to define the leveling of a data set. And we think that this approach may be also equally applicable to other dynamical astronomical data sets. And we repurposed the model to perform a task which it was not initially trained for. And when it succeeds in such task which is higher level than the original classification task, it just uh, increases the transparency of the entire process, right? So this is more like a post hoc technique uh, to really decode the working of a black box deep learning model. So we are doing saliency analysis to understand whether the model is looking at the right region where the emergence is happening. Also, it is understanding the dynamics or evolution of the active regions to understand when in time the emergence is happening. Um, and also because we have the ensemble of models instead of a single model, it can really help us understand how much you can trust in the model prediction. And it is especially important because we have a limited data set, right? So it is very much possible that the limited data set will have class imbalances, and also it will not represent the entire population of the emergences. So instead of using a single model uh, to give point estimate, the ensemble of models actually gives us the whole to capture the diversity in the training data set, and generalize better, or um, give you a trust score, right? And this work has been recently accepted, and also we have the data catalog published. So our future works being this. So we want to include also other surveys to make a more diverse data set. Other surveys, for example, can be the SOHO HMI dataset. But before that, we need to homogenize the data sets, right? So that we can retrain these models to expand uh, on 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 several surveys, right? Um, and we are also thinking of a more ambitious task of um looking at the early evolution of these active regions to understand whether flux emergence is going to happen, whether there is a temporal connect. Uh, and as I said, it can be worth applying such approach to other astronomical dataset, especially the ones where we don't trust the initial level. We can train a model and then we can refine the levels to arrive at a very high quality dataset at the end, at the point of convergence, right? And So this is another like work that we are currently doing. So I just talked about emergence and non-emergence, but within emergence and non-emergence there are different varieties of active region evolutions, right? So we are trying to understand how is the class imbalance, which type of emergences happen more frequently in our dataset and which are more rare in the dataset. With this approach, we can actually create a model which can separate these classes into more finer subclasses. And also this understanding of this data imbalance here will help us to create ensemble of models, right? So we are currently working on another project which is on solar energetic particles forecast. So there, because there is a big imbalance between these positives and negatives, we are actually utilizing that imbalance to create an ensemble of models, right? And that similar approach can be also applicable for this, right? To get a uh, more refined set of ensembles which will give us this multi-level classification outcomes with uncertainties. So with that, I will end and I'll be happy to answer any question you have. And this is the QR code of the published dataset that we have from this MDI active region evolution videos. Thank you so much.
Thank you, Shubhamar, for a very nice talk. Now we open the room for questions, and anyone can just jump in and ask your question or raise a hand or write in the chat. Matthias.
Yeah, thank you very much for this very interesting talk. So my
Thank you.
question is, so on the Sun, flux emergence seems to happen over a wide range of scales. Active region is
Sure.
kind of the largest part of it, and I mean, most of it seems to be connected kind of with the power law. So there's some scale invariance in it.
Right. Yes.
Do you think your neural network would work over a wider range of scales, even though it's mostly trained on active regions, or are there differences if you would go to smaller scale flux?
So actually, we are doing some experiments on that. Suppose we have a small active region, you can blow up the size, right? And then you can utilize the same model to identify those small scale emergences. And we were surprised to see that even the model was able to detect the small little flux emergences. So maybe it is because it is a natural extension of this work because of the fact that they are scale invariant, and this model could be really repurposed to identify the small scale emergences.
Peter and then Sarah. Peter, you are mute.
I'm curious to know what scientific questions you would most like to address with this method as it applies to surface magnetic fields on the Sun. You didn't say much about that.
So for this particular work, our objective was entirely to refine or to create a classifier that can correctly understand whether an emergence happens or not within a video. But to build that classifier, we found few obstacles, and when we were dealing with those obstacles, we developed these procedures that I have discussed in this. But so that was kind of the drive for this particular work, to actually start with a crude data set and then refine those leveling, and for that we developed this technique. And we also if when you arrive at such cleaned, refined data set, whether you can repurpose to the model to do higher level tasks. So that was the entire objective of the of this particular work. But of course, as I was showing in this particular diagram, so there are different types of emergences, and when we manually verified the dataset, we found the biases in the dataset, and we can utilize this finer demarcations to answer further science questions that may have that we may have in future.
Sarah?
Very nice talk. So I
Thank
actually
you.
want to follow up on Matthias's question and
Right.
ask, do you think it would be possible to use this? You were saying that you could actually apply it on a smaller structure, and maybe that means it's scale invariant. Could you use this technique to diagnose how the degree to which it is scale invariant, going to higher and higher resolution, smaller scales, maybe using DKIS data in the future?
Probably yes. Yeah. So basically, on the only thing we will need is homogenization of the data, right? Because these data sets will have different noise levels, different resolutions, etc. So once we do that, we can do several tweaks to the data to bring them into equal footing, and then try and apply this method to see when or where it breaks, right?
Yeah.
So as you were saying, so until which resolution we can utilize and leverage this approach, and we can really find where it breaks.
Very interesting. Thanks.
No problem.
Other questions? So I have a question
Yeah,
on
sure.
whether you can detect pre-emergence features by applying this technique.
So yeah, that is the question we are also trying to answer at this moment. So whether looking at the pre-emergence evolution, we can predict the emergence, or how early we can go in time to understand the temporal connects, right? Yeah, that is something we are currently working on. But this was not about prediction. This is like, given the emergence happens in the video, or it did not happen in the video, whether the model is correctly and like model is able to provide the correct level to that video. Yeah, it is providing the correct prediction, a correct identification whether the emergence happens or not. So it is not predicting whether this emergence is going to happen. It is just classifying the videos into two different types, given that the video already covers that emergence.
Thank you. Other questions? If not, let's thank our speaker again for a very nice talk. Thank you
Thank you.
so much.
Thank you.